In this video, we are going to talk about Taylor series, which you learned about in first-year calculus, as well as vector or multivariable calculus, and now we're going to learn about it in complex analysis or complex calculus. So the amazing thing about the Taylor series is it tells you that a function, as long as it's analytic, that we can represent it using a power series, and this power series is just a polynomial. So you can represent any analytic function with a polynomial. Now, how close of an approximation this polynomial is really depends on how many terms you're willing to write out. There are a couple of other things to note about how good your estimate is. One, we're talking about f being analytic throughout a disk, and the series will converge as long as the point that you're trying to estimate lies within the disk where f is analytic. And second, we choose where to center our approximation. That's our z0, the center of our disk. This is where our approximation is best. As we move further away from z0 within our radius where we're analytic, but as we move away from z0, our approximation becomes less and less accurate. So once we know the series converges and we're in the proper area of our disk and close to our center, then we can get arbitrarily close to estimating this function with a polynomial. In first-year calculus, also vector analysis, you probably did error analysis to see how close your function actually was. We're not going to be doing that in this class. But what we will be doing later in this class is we'll be using these Taylor series along with Cauchy's residue theorem to solve different complex integrals. This is my overview slide for this video. We'll spend a few more minutes going through this slide before we go through each topic in more detail and in more examples. We have this example here. If f of z equals e to the z, we want to find the Maclaurin series representation at z equals z0. And a Maclaurin series is a Taylor series centered at z equals 0. So z0 is equal to 0. These are these z0s here, and these z0s as well. So we calculate, we need to have f of z0, f prime of z0, f double prime of z0, f triple prime of z0, etc. So f of z is equal to e to the z. So f prime of z is also equal to e to the z. Basically, the nth derivative is equal to e to the z. And then evaluated at z0, because that's what this part of the formula requires, our derivatives evaluated at z0, which is equal to 0, is equal to, so we plug in 0, it's equal to 1. So e to the 0 is equal to 1. So now we can plug in to our Taylor series formula. We have f of z0, which is equal to 1, plus f prime at z0 over 1, which is equal to 1 times z0. And then we have f double prime of z0 over 2 factorial times z minus z0 squared. So our f double prime at z0, again, is equal to 1 over 2 factorial z minus z0. This is just a 0, so that's z squared. And you might see the pattern here, or you might do a couple of more terms, your f triple prime over 3 factorial, right, using this formula. F triple prime would be next over 3 factorial z minus z0. So, but the pattern is going to be that we have a summation n equals 0 to infinity, 0 to the n over n factorial. So e to the z can be represented by the polynomial n equals 0 to infinity, z to the n over n factorial. When we go to the chapter concerning residues and Cauchy's theorem about residues and complex integrals, we're going to want to convert certain expressions into a Maclaurin series or other type of series expansion. And so the idea is we take some of these known series expansions and maybe use this extra identity here, but we take these known series expansion, compare them to the series we want, and somehow we want to manipulate these formulas here until we get the series we want. The manipulations we can do are, for example, replacing z with a simple function of z like 3z and z minus 1. So here we might replace z with 3z. If we do that, we have to replace this z with 3z. Or similarly here, we could replace this z with 3z, but then we'd have to replace this part with 3z as well. And the idea is z, this formula is for z a complex number. It certainly holds for 3 times z, similarly for this expression. The other thing we can do is multiply the entire equation by a value. So, multiply everything by 2, for example, both sides of the equation. Or we can do term-by-term differentiation. We'll treat factorials as constants and leave summation indices alone. So just each term, we're going to take the derivative. Or we can make adjustments to the summation indices. So we'll do an example to kind of put this on more in better context. The example is we want to represent z squared e to the 3z as in a Maclaurin series. So we can start off by choosing one of these three and then manipulate it until it looks like this. And as you can see, this sort of looks most similar to e to the z. So we're going to use e to the z equals n equals 0 to infinity, z to the n over n factorial to find a representation for z squared e to the 3z. So the first step is, if I compare these two, is, well, here my e exponent is 3z, not just z, but I can replace z with a simple function of z like 3z, so I do that. So I have, replacing these z's with 3z, I get e to the 3z equals n equals 0 to infinity, 3z to the n over n factorial. Now I look at this and I compare it, and I need to multiply by z squared, and I can do that too, multiply the entire equation by a value. So now I have z squared e to the 3z equals n equals 0 to infinity. I have 3 to the n over n factorial, but now I have z to the n plus a z squared, so that will give me a z to the n plus 2. Now I do actually have a series representation now of what I wanted, the z squared e to the 3z, but often we want this z to the n, this exponent on z to be raised to the n. So I can walk back my indice of my summation so that I start at n equals 2, so that here this will be, I can have z to the n. If I start at n equals 2, I need to subtract basically 2 from all my indices. So I can think of this here as replacing n with n minus 2. That is our overview, and now we can go into more detail, more examples. We start by looking at the conditions of the theorem. So suppose that a function f is analytic throughout a disk, z minus z naught is less than r naught centered at z naught with radius r naught. There's a lot of knots, but anyway. So first, what does it mean for a function to be analytic? So a function f of a complex variable z is analytic at a point z naught if it has a derivative at each point in some neighborhood of z naught. So what is a neighborhood of z naught? It is exactly this disk. So this disk, as you can see, z minus z naught is less than r, but it's less than, strictly less than. It's the interior of this circle. So it's centered at z naught. Here's my z naught. Has a radius of r naught, and then we've got this circle, and I dotted the boundary because the radius is the boundary is not included. It's strictly less than r naught, and that's considered a neighborhood. The neighborhood r naught can get as small as you like. And again, it's called a disk instead of a circle because a circle technically is the border that is dotted, and the disk is the interior. And the idea of this neighborhood or this disk, it's the equivalent of in calculus, first year calculus, when you looked at x and you wanted things to behave kind of in a small interval, an open interval around x. This is the disk is a two-dimensional equivalent of this open interval, right? Because complex variables are two-dimensional. If you recall, in chapter 2, we had a video where we talked about how we can prove that a function is analytic. We had this theorem here that had 3 conditions. First, if we rewrote our function f of z in this form, u of xy plus I v of xy, where u is the real part of our function, and then v of xy was the portion that gets multiplied by I. then we said first, the first order partial derivatives of the functions u of xy and v of xy with respect to x and y exist everywhere in the neighborhood. So we take the partial of u with respect to x, we take the partial u with respect to y, we take the partial of v with respect to x, and we take the partial of v with respect to y, and they should exist everywhere in our neighborhood around our z naught. And 2, those partial derivatives need to be continuous. And then 3, the partial derivatives need to satisfy the Cauchy-Riemann equations, whereas the partial derivative of u with respect to x is equal to the partial of v with respect to y, and the partial of u with respect to y is equal to the partial of v with respect to x. So this is technically how you prove a function is analytic, but actually that's a very formal proof. Usually we just look and make sure that we don't do division by 0. And one more comment. When we say we are centering our approximation at z naught, what we are saying is z naught is where we have the best approximation. And in a small neighborhood around z naught, we can expect a fairly decent approximation. As we move further away from z naught, we expect more and more error. But z naught is where we expect the best approximation, and hence we call it the center of our approximation. Okay, so finishing reading our theorem. So we have a function f. It's analytic throughout a disk, and it's centered at z naught and with radius r naught. Then f of z has the power series representation. F of z is equal to the summation from n equals 0 to infinity, a to the n, times z minus z naught raised to the n. And here we have our formula for our a to the n coefficients. So a to the n is equal to the nth derivative of f, evaluated at z naught, divided by n factorial. I can expand this definition out. So when n is equal to 0, we have a sub 0, which is equal to the 0th derivative. That means that's the function f, evaluated at z naught, divided by n factorial. 0 factorial is 1. So far we have f of z naught, and then we have z minus z minus z naught raised to the 0 power. Anything raised to the 0 power is 1, so we're just left with f of z naught. For n equals 1, for a n, we're going to have the first derivative, f prime of z naught, divided by 1 factorial, which is just 1, times z minus z naught raised to the first power. For n equals 2, over here, a n, we're going to have the second derivative of f evaluated at z naught, f double prime of z naught, divided by 2 factorial, times z minus z naught raised to the second power. For n equals 3, again, we have the third derivative evaluated at z naught over 3 factorial times z minus z naught raised to the third power. And hopefully you can see the pattern from here. A couple of notes. Any function which is analytic at a point z naught must have a Taylor series about z naught. And the second note is we call a Taylor series centered at z equals 0. So when z naught is equal to 0, this centering here, if z naught is equal to 0, it is called a Maclaurin series. Our first example is to find the Maclaurin series representation at z equals 0 of f of z equals e to the z. And I'm going to start just again by expanding this formula out. So for n equals 0, we have our an is equal to f to the 0th derivative, which is just f. So we have f of z, and then z minus z naught to the 0, which is just 1. Plus, when n equals 1, we have the first derivative of evaluated at z naught over 1 factorial z minus z naught to the first power. Then we have, when n equals 2, we have f double prime evaluated at z naught over 2 factorial z minus z naught squared. And then our third term, when n equals 3, we're going to have the triple integral, the triple derivative evaluated at z naught over 3 factorial z minus z naught raised to the third power. So you can see first I need to know what f of z naught, f prime of z naught is, f double prime at z naught, etc. So f of z is equal to e to the z. The first derivative is equal to e to the z, and actually the nth derivative is still equal to e to the z. So the nth derivative of e to the z evaluated at z equals 0, so we have e to the 0, which is equal to 1. I switched the position of my f of z and my expanded form here, so I can just plug in. So when I have z f evaluated at z naught, that's just going to equal to 1, and this is also anything to the 0 power is just 1. Here I have f prime evaluated at z naught, again that's 1 over 1 factorial, which is 1, and z minus z naught is just z. F double prime, so that's also 1 over 2 factorial, z minus z naught, again z naught is 0, so that would be z squared, plus f triple prime is just 1 over 3 factorial, z cubed, plus, and your nth term is just going to be 1 over n factorial, z to the n, if you just look at this pattern here. So in other words, f of z is the summation from n equals 0 to infinity, z to the n over n factorial. And so I can represent e to the z as this summation, as this series. As I mentioned in our overview, so this is an amazing thing to be able to do, to write any analytic function in terms of a polynomial, z to the n over n factorial. But our main use of the Taylor series and the Maclaurin series is to write other functions in terms of a Maclaurin series. So the techniques we're going to use is we start with a function like e to the z, which is equal to, which we just found was equal to z to the n over n factorial. Another good function to know, so you should definitely remember these, is 1 over 1 minus z is equal to the summation n equals 0 to infinity z to the n. And then the last one I think is really critical to remember is sine of z is equal to e to the iz minus e to the minus iz over 2I. And we start with these functions and we manipulate them until we get to the function we want. And we can manipulate them by, one, replacing z in these formulas with a simple function of z, something like 3z or z minus 1, or I times z. Or we can multiply the entire equation by a value, or we can do term-by-term differentiation, treating factorials as constants, and we leave summation indices alone. Or we can make adjustments to summation indices. And this is the example we will do. And we start with an easy example. We want to use this equation here, the one we just developed, e to the z equals summation n equals 0 to infinity z to the n over n factorial, to find a representation for z squared e to the 3z. So we can start here. Well, we can look at this and we can say, okay, one of the things we can do, and there are many orders, you can do this different ways, but this is how I see it. So the first thing we can do is replace this z in our formula with 3z, so that we're starting to get this e to the z looking like this. So we're going to replace z with 3z. So here we have e, now 3z equals n to equal 0 to infinity. Here's another z, which we need to replace, so 3z to the n over n factorial. And again, this should be totally valid in this formula. Since this is e to some complex number, we certainly can multiply the complex number by 3, and we should still be able to use this formula. So that's perfectly fine. The next thing we're going to do, comparing these two, well, actually now I need to compare these two. I have e to the 3z, but I need to multiply by z squared, and I can do that. I can multiply the entire equation by the value of z squared. So multiplying this by z squared, I get z squared e to the 3z equals n equals 0 to infinity. Now I have my 3 to the n, and I have my n factorial. I have z to the n, but I also have another factor, z squared, so that will give me z to the n plus 2. So I right now do have a series expansion for z squared e to the 3z. But normally we like this to be in terms of n. So we can do one more step, which is to make adjustments to the summation indice. If we start at n equals 2, that means we'll need to, since we kind of advanced our summation by 2, we need to walk back all of these n's by 2, or we can think of this as just replacing n with n minus 2. So here we get 3 to the n minus 2, n minus 2 factorial, z to the n. So this is our final representation, a Maclaurin series representation of z squared e to the 3z. For our next example, we're going to use this formula here, sine of z equals e to the iz minus e to the minus iz over 2I, to find the Maclaurin series expansion of f of z equals sine of z. So I have written sine of z equals 1 over 2I e to the iz minus e to the minus iz, which we were given, and then I can use my formula. My e to the z, Maclaurin expansion, is equal to z to the n over n factorial, where I replace z with iz, which is what I have here. So I'm going to have e to the iz is equal to summation n equals 0 to infinity iz to the n over n factorial minus summation from 0 to infinity minus iz to the n factorial. This next line is just algebra. Here I took out the minus 1 to the n so that I'm left with iz to the n, and then since I have both terms iz to the n now, I can have, this would be 1 minus 1 to the n times my I z to the n, which is just I to the n, z to the n over n factorial. I can further simplify this since what's in these brackets, the 1 minus negative 1 to the n is equal to 0 when n is even, so I can replace n with 2n plus 1. So if I look at this term here, 1 minus 1, 2n plus 1, well, that's equal to 2. So right when n is odd, this is 2. And I, 2n plus 1, will be equal to minus 1 to the n times I. So I replace these two in my formula, and I get sine of z is equal to 1 over 2i summation 2 to the minus 1 to the n times I, z to the n plus 2 over n plus 1 factorial. I'm sorry, this is n plus 1 factorial. Our next example is to use the result from our last example, which is sine z equals n equals 0 to infinity, negative 1 to the n, z to the n, 2n plus 1 over 2n plus 1 factorial, to show that cosine has the expansion n equals 0 to infinity, negative 1 to the n, z to the 2n over 2n factorial. And the first thing to notice is how sine and cosine are related. And looking at these techniques, they're related by differentiation. So I start with sine of z equals n to the 0 to infinity, negative 1 to the n, z to the 2n plus 1, 2n plus 1 factorial. So what I can do is differentiate both sides of the equation. And over here, so this is a summation. So if we have a function and we add it to another function, and then we want to take the derivative, then that's just equal to the derivative of the first function plus the derivative of the second function. So in other words, we can do term by term differentiation. So we just sum, we take the constants out, the minus 1 to the n, the 2n plus 1 factorial, those are our constants because we're taking with respect to z. So we're taking the derivative of z to the 2n plus 1 term by term. And that's going to give us our 2n plus 1 comes down as in front over, we still have our n plus 1, and then this exponent gets reduced by 1, so that's 2n. So I still have my minus 1 to the n. I move this over here with my 2n plus 1, subtract 1 from the exponent. But this, just because of factorials, this 2n minus 1 factorial is equal to 2n plus 1 times n factorial. So these two can cancel out, and I get my minus 1 to the n, 1 over 2 to the n factorial, z to the 2n, which is exactly what I wanted to show. This next example seems really typical of what you'll be doing a lot in that residue chapter with Cauchy theorem of residues. So it's something that you want to pay attention to and kind of get a feel for. So we want to expand the function f of z equals 1 plus 2 to the z squared over z cubed plus z to the fifth, which is given to you by your book as 1 over z to the third, 2 minus 1 over 2 plus z squared. So you want to expand this into a series with powers of z. And for my own sake, I just wanted to be able to verify algebraically that this equation holds. Of course, it's just algebra, but I went ahead and did the algebra here, so I'll let you take a look. So once you have the algebra confirmed, I took this portion because this is the book is sort of giving you the form that's easier to expand into a series of power of z. So I took the 1 over z cubed times 2 minus 1 over 1 plus z squared. So the z cubed, it's factored out because this is in powers of z. If this is also in powers of z, we can certainly multiply a power of z times a power of z and figure out what the new power of z is. Certainly we could do this with 2. That's easy. So this is the part, this term here is what we need to work on. And looking over here, this term is closest to this formula here. In other words, what I have here, this 1 plus z squared, looks a lot like the 1 over 1 minus z if I can replace this z here with a simple function like minus z squared. So I've written this formula down. 1 over 1 minus z equals n equals 0 to infinity, z to the n, and I want to replace the z on both sides of the equation by minus z squared. And what that is going to give me is 1 plus z squared equals summation n equals 0 to infinity, my minus z squared to the n. So that's exactly what I'm going to plug in. So I have my 1 over z cubed, I have my 2 and my minus, and then here I'm going to plug in this formula here, 0 to infinity, my minus z squared to the n. From there, I use some algebra. I factor out my -1, and I get z to the 2n here. And I can actually start expanding this out. So I have my 1 over z cubed. Again, this is a nice function of powers of z. And then I have my 2. When I have n equals 0, this is -1 to the 0 power, which is 1, and z to the 0 power, which is 1. So I have my -1. And then when I have n equals 1, this becomes -1, but combined with this negative, I get a positive. N equals 1, then I get z squared. N equals 2, so this becomes a positive 1, but I have this negative, so there's a minus. N equals 2, then I would get z to the fourth. And I can keep on plugging in more values, but what I get is 1 over z cubed times 1. I already combined my 2 minus 1 times 1. 1 over z cubed times z squared, which leaves me with 1 over z. My 1 over z cubed times z to the fourth, which is going to leave me, my minus z. And if I had expanded this out, I'll see my next terms are going to be z cubed minus z to the fifth. So here is a series of powers of z, and that's exactly what I was asked to show or find. I do have a note about this series formula here that we use. The 1 over 1 minus z is equal to the summation n equals 0 to infinity z to the n. And the note is that the convergence, the radius of convergence, is absolute value of z is less than 1. So when you are not within this disk, this series does not converge, and your Taylor series, your Maclaurin series won't be of much use. So what to do when you are outside this disk, that's a problem that we will look at later when we're looking at Cauchy residue theorems and also evaluating more complex integrals. So be warned, this topic is not going to go away once you finish this chapter. It will come back, so it's worth your effort to learn it well. Now we can review the main points of our video. So we talked about Taylor series, and what a Taylor series allows you to do is take an analytic function and then write a power series representation of that. In other words, you can represent it as a polynomial, so z to the n, where we're centered about z naught, so z minus z naught to the n, with a coefficient equal to f to the nth derivative of f evaluated at z naught divided by n factorial. And then we sum up all of these terms. We did a quick example. For f of z equals e to the z, we can find the Maclaurin series representation at z equals 0. And a Maclaurin series representation is just a Taylor series centered at z equals 0. In other words, the z naught is equal to 0. And what we noted first is that we use our formula here for the Taylor series, and we do need to have f evaluated at z naught, in this case z naught is 0, f prime evaluated at z naught, f double prime evaluated at z naught, and all the derivatives evaluated at z naught. So we looked at f of z, and we found that the nth derivative of f of z is always equal to e to the z. So evaluated at 0, all of our derivatives are equal to 1. So now we can plug into the formula. F of z naught is equal to 1. Then we have our derivative, first derivative of f at z naught over n factorial, and this is n equals 1, so that's 1, z minus z naught raised to the first power. So that will give us our z. Here we have our f double prime at z naught, which is also just 1 over 2 factorial, z minus z naught, and this is just z squared. And so we found the pattern that this is equal to the summation n equals 0 to infinity z to the n over n factorial. So this was our formula, our series representation, our power series representation of e to the z. And this is, on its own is a valid topic on its own, because it's pretty incredible to represent any analytic function as a polynomial. But we did mention, or I did mention, that later on in the book, when we start talking about residues and Cauchy theorems concerning residues and integrations around curves, that we often want to represent our expression in terms of a series. So we looked at that in terms of Maclaurin series, and I have two series to kind of start us with, which is the one we first found over here, e to the z equals n equals 0 to infinity, z to the n over n factorial. And I gave you another series, 1 over 1 minus z is equal to n equals 0 to infinity, z to the n. And I also gave you this formula here, which turns out to be quite handy. Sine of z is equal to e to the iz minus e to the minus iz over 2i. And the idea is if we have an expression that we want to make into a series expansion, we try to find something that's similar in form. And then once we find something that's similar in form, we manipulate this formula until it looks like our expression. And the things we can do to manipulate it is to replace these z's in the formula with simple functions of z's, like 3z or z minus 1. Or we can multiply the entire equation by a value, or we can term by term differentiate, or we can make adjustments to the summation indices. So for an example, if we wanted to find a representation for z squared e to the 3z, looking at these two forms, this is the one that looks most similar. And the first thing, well, you could start with multiplying everything by z squared, which is just fine. But the first thing I did is said, okay, instead of a z to the n, I want, instead of e to the z, I want e to the 3z. So I'm going to replace z in this formula with 3z. So I'll have e to the 3z summation 3z to the n over n factorial. So that's what I did exactly here. E to the 3z summation 3z to the n over n factorial. The second thing is, this is getting closer to looking what our expression, but we need to multiply everything by z squared. So I multiplied this entire formula by z squared. So now I do have an expression for a series representation in terms of powers of z. But I did one other simplification, because often we like this formula to start at z to the n. So I I increased my indice of my series to n equals 2, which means this then needs to start at z equals n, right? And then these also have to be, I have to subtract 2 from each. Or I can think of this as replacing n with n minus 2. So that's our summary. For review, I have these two problems for you to try, which is to derive a series representation for 1 over 1 plus z. And also, the second problem is to derive a series representation for 1 over z. I know this looks strange, just, figure out which form it looks most like and then try to convert it to a series representation. I suggest you pause the video, give the problems a try, and when you come back, I'll have solutions for you. Here are the solutions for the two problems. And that's it for this video. Thank you for watching.